In this video, we're going to talk about operations with decimals, and we're going to go through the four math operations: addition, subtraction, multiplication, division. And for each of them, we'll do a visual, and then we'll talk about how to do it without visualizing. And the book calls this the pencil and paper algorithm. I think it's kind of funny that they bring that up now, but they didn't bring it up with fractions. All right, that's fine. Okay, so first thing we're going to do the visual. All right. So with addition, it's kind of not exciting. like it's you represent and count what you got. So let's see. 2.1 plus 3.4. Let's do this. Okay, so I'm going to do two whole squares and then 0.1 of an additional square, which I'll have to go ahead and divide up into tenths. Wow, that's so sloppy. I'm sorry. I don't know why I'm getting hung up on it, but it's fine. Okay, so I actually want to switch to my yellow highlighter because it's a little bit easier to see. Thank you. So 1, 2, and then 0.1. Okay, combining that with 3.4. Okay, so 3 whole squares. Notice I'm being lazy about the whole squares, right? I could technically, and I'm sure the book does, divide them up into tenths, since we had to divide one of them up into tenths, but I'm being lazy, and you can be lazy too. Okay, 3 whole. And then we'll have to do again tenths on the last one and shade in 4. All right, there we go. 1, 2, 3, 4. Okay, and then we count up what we have. So in this case, 5 whole numbers. And then it looks like of the tenths, we have 5 tenths. So we represent that as 0.5. So 5.5. So exciting. Okay, for the actual algorithm approach, and I'm going to write down pencil and paper algorithm because that's what they do refer to it in the textbook, but not really. I don't remember if they do in the homework. Oh, sorry, pencil and paper algorithm. I don't remember if they do in the homework problems themselves, but that's okay. I just want to kind of at least write it down once. We'll write the steps. So for addition with decimals, we need to line up the decimals or decimal places. I'm going to be a little bit lazy in the way I said that. Line up the decimals, the decimal points. We may want to add zeros where necessary. That typically comes more into play when we do subtraction, because we're going to use the exact same rules for subtraction. Okay. And then we need to bring the decimal straight down into the answer. Awesome. All right. So let's do an example where we use this approach. Let's do 4.039 plus 17.18. Now, it's wise to just be in the habit of putting the larger number first, mainly because of subtraction. We might have to remind ourselves of that. In fact, we'll do one where you have to remember to do that. But we're going to start with 17.18. I'm going to line the 4 up under the 7, the decimal, and then 0, 3, 9. And as you can see, this is where we would want to maybe add a 0 there above the 9, especially for the visual aspect. It kind of helps line up the numbers. And if you get a little sloppy like me, might be useful, but it's also really useful for students to kind of see it that way. Okay, so 0 plus 9 is 9. 8 plus 3 is 11. Carry the 1. That's 2. I know they don't use the phrase carry anymore, but I can't remember what the one they use is. And there we go. 21.219. So exciting. All right. Subtraction. So with subtraction, the visual is a little bit annoying when you have to draw it. You may want to kind of give yourself some decent enough space. I know that when I've tried drawing this, I can get a little bit terrible at it. All right, so let's say we want to do, oh, sorry, I meant to write the word visual. Let's say we want to do 5.6 minus 4.1. So we'll start with writing out or drawing 5.6, okay? Visually representing it. And we'll be lazy and use blank boxes for the whole numbers. 3, 4. Give myself more space. 5. Each box is looking worse than the previous. Let me actually attempt to make it look slightly square. There we go. All right. And then the last one, we will have to shade or divide it up and then shade 6 of them if we're representing 5.6. Okay, so oops, sorry. Try to be a little bit neater. I think I'll have to add some here. There's 5, 6, 7, 8, 9, and 10. Okay, so I had to do it that way. It's fine. Five whole numbers. 6 of these little rectangles. All right, cool. All right, so then for the subtraction element, we literally are going to remove 4 of these squares, 4 whole numbers. So I'll just put an X through them. And then 1 of the tenths. So I'm going to attempt to do like a skinny X. Surface Go does not want me to do a nice diagonal. It just hates diagonals. That's why they always look crooked. It's fine. You can just think I have a shaky hand. I don't really care. And then what we're left with is 1 whole number and 5/10. I intentionally kind of wrote it like that, fractions, because I want us to kind of remember the connection to fractions, because there you're going to bring that up later. Okay, so 1.5 would be how we would write that final answer. All right. Let's do the paper pencil algorithm. Wow, sorry, pencil and paper algorithm. Okay, so same, it's the exact same as addition. I will write it down, but you could be lazy and just say same as addition. Line up the decimals. Don't get too sloppy there, Allison. Add zeros where necessary. Bring, that's not a B. Bring decimal down into answer. I know I kind of worded it slightly different above, like I think it said straight into the answer or something like that, but it's fine. You get the idea. Let's try. 15.6 minus 2.743. Okay, they gave it to us nicely where we have the larger number first. So I'm going to put the 15.6 And line the 2 up under the 5, 7 under the 6, and then 4, 3 are kind of floating over here. So I'll add a couple zeros. So then to actually subtract, we will need to borrow. I believe they use the phrase regroup, but I remember the old school borrow for right now. So I'll have to, technically it makes the next column a tens place, but I'm going to borrow from that. So it's 9. I'm sorry, a 10, not tens place. Well, it is in the tens place, but it makes it a 9. And then the last one becomes a 10. Okay, so 10 minus 3 is 7. 9 minus 4 is 5. And then I can't do 5 minus 7. I have to borrow or regroup again. 15 minus 7 is 8. 4 minus 2 is 2 and 1. So 12.857. Okay. Let's do one where we have to think about it a little bit. Negative 4.6 plus 7.3. Now, visually, I see a negative and a positive, which means when we talked about integers in chapter 5, we're going to subtract the two numbers. So because I'm going to subtract, I'm going to go ahead and put the bigger number first, which is 7.3, and minus the 4.6. Don't need to add any zeros. Do need to borrow / regroup. 13 minus 6 is 8. 6 minus 4 is 2. And then the answer is positive because the bigger number is positive. This would be the exact same approach if they had switched it. In other words, if it had been negative 7.3 plus 4.6. I still would have done the work just like I did above. I would just throw a negative on in the answer because the bigger number is negative. So I'd still show the exact same work. Okay, that's how we would kind of approach that. All right. Moving on to multiplication. Remember, multiplication is repeated addition. So that's how they kind of approach the visual. The first visual they kind of show is repeated addition. So let me go ahead and show that. So typically we would use this when maybe we have a decimal mixed with a whole number, like this, 2 times 0.7. So for this, we're going to do 0.7 twice. Okay, so I'll start with 0.7. I'm going to actually try to give myself enough space to see. So, okay. And then 1, 2, 3, 4. All right. Shading. Oh, sorry, pressed it too long. Shading the columns, 7 of them. All right, cool. There we go. Now, rather than actually draw this exact same thing again, they do this kind of overlay. And the reason they do that is to show when we hit a whole number, okay? So having a second color is kind of useful, like I do. And then I kind of just offset it a little bit. Okay, wow. I did a terrible job of drawing those last ones. I'm gonna actually fix it really quick, sorry. That first one was just off anyways. There we go. I mean, I know they're kind of crooked, but still. Kind of helps when they line up. 3, all right. 4, 5, 6, 7, 8, 9, and one more gives me 10. Okay, and then I'm still gonna go ahead and highlight 7 of them. But the idea is we can visually now see that this kind of overlap part makes up one whole. And then we have an additional, sorry, I should have done that in blue, an additional, there, 4/10 left over. All right, so this comes out to 1.4. They do have a different approach when you're multiplying two decimals. And it does require a little bit more work to count it all up. So let's give it a shot. 2.3 times 1.7. So both decimals. For this, rather than use the repeated addition approach, they use the rectangle approach where they draw a rectangle represented as a 2.3 on one side and 1.7 on the other. Okay. All right. So here, we're going to do this. 2.3. So two whole numbers or two whole boxes. And then 3/10 at the end. Great. And then down this way, 1.7, we would have one whole box, 7/10 at the end. Wow, I'm trying not to make these super big because it'll just take up so much space. Come on, there we go. Did I get 7? 1, 2, 3, 4, 5, 6. Nope, one more. 7. All right, there we go. Okay, and then we kind of center the whole, or I should say, draw the whole thing out. All right, now here's what we kind of do. Because these are technically just continuing on here. I'm going to go ahead and draw them all the way across, and then I'll draw these ones down. Okay. So what we're going to kind of do, there's a couple ways to approach it. The book approaches it a tiny bit differently than the way I'm going to do it. I'm going to approach it based on what I kind of see visually. I see whole numbers, like the whole square, and then I see tenths, and then I see hundredths, right? Those little squares in the corner are hundredths. So I'm going to kind of think of it that way. So I have two whole numbers. Two. Okay. So for the tenths, when I count them up, let's see. There are 7 here. So then there would be another 7. So that's a total of 14 plus these 3. So that's 17/10. Here, I'm going to do this actually in red, not blue on that one too. Okay. 17/10. Okay. So here, I'm going to use the fraction approach, 17/10, because I want us to see 17/10 technically is actually 1.7. Do we see that? Right? Because it's a 10 plus a 7, right? So the 10 over the 10 becomes a whole number, and then the 0.7. So here, I'll just write out what I just said, 10 over 10 plus 7 over 10. That's where the 1.7 is coming from. Okay. You don't need to do that. You can just notice that 17/10 is 1.7. Okay, nothing wrong with that. And then the hundredths, so those last little squares, there should be 7 by 3, so 21 of those. So 21 hundredths would be 0.21. Okay, so basically what I'm doing is I'm going to add up the 2 plus the 1.7 plus the 0.21. So 2 and the 1.7 gives me 3.7 plus the 0.21. That's going to be 3.91. And there you go. Okay, cool. So there are the way we can represent the multiplication visuals. Okay, so for the pencil and paper algorithm, and here I'm going to be a little lazy and put pencil and paper and not put the word algorithm. All right. You actually multiply like normal. Oops, that's not how you spell the word multiply. Multiply like normal. And then we have to count how many actual digits are behind the decimal, or numbers are behind each decimal in each part. Okay. So count I don't know if you hear a Christmas carol playing in the background. That's because I have a clock on my counter, a Christmas clock that plays every hour. Count how many, I'll say digits. I'm going to use the word digit. Count how many digits are behind decimals. And the reason is because in a second, I'm going to use the word number. And then place the same number of digits behind the decimal in the answer. I really feel like writing this out isn't nearly as clear as actually doing a problem. Okay. So let's try. Let's do 1.8 times, sorry, lost my page, 0.473, sorry, lost track of where I was on the page. Okay, 0.473. All right, so I'm gonna, just for the sake of ease, I'm gonna drop the 0 in front of the 0.473. And in fact, they often drop them just for ease as well. And I'm gonna go ahead and write the bigger of, in terms of number of digits first. So I'm gonna take the 0.473 and write it first, just because there's more numbers literally. And then the 1.8. So I don't need to line up the decimals. In fact, you can ignore the decimals if you wanted to. You could just do 473 times 18. You really could. So what we're doing is we're just going to straight up multiply. So 8 times 3, 24. Carry the 2. 8 times 7 is 56. Plus 2 is 58. 8 times 4 is 32. Plus 5 is 37. Great. Next number, add a 0, because we're now in the tens, or the next number place. Okay, tens place. 1 times 3, 1 times 7, 1 times 4. Boring. Okay, cool. Add them together. 4, 11, 15, and 8. Okay. And then here's where the magic happens, because I just ignored the decimals. I'm going to place the decimal in the answer based on where the decimals were in the original problem. So in the first number, 8 was behind the decimal, so 1 digit behind the decimal. In the second number, 4, 7, and 3 were all behind the decimal, so there was 3 digits behind the decimal, for a total of 4 digits behind the decimal. So I'm going to place the decimal in front of the 8. That way, 4 numbers or digits are behind the decimal. And that's the answer. I could put the 0 back in front if I feel like it. But 0.8514. Wow, I am just, Surface Go does not want to cooperate with me tonight. It's fine. We will keep struggling in an epic struggle. Okay, I do want to note really quick, they kind of make a note about the fraction aspect of this into justifying why we take the approach that we just kind of ignore the decimals. Like literally, you could have just done 473 times 18. Like you did not have to write the decimals. Okay. And the reason is, if we were to think of these as two fractions, 1.8, and this is where they kind of do that trick where they think of it as 18 tenths, rather than write it as a mixed number. They're writing it as an improper fraction. Are you gonna actually do the second part? There we go. And then times 473 thousandths. 473 thousandths. Okay. And so when you multiply fractions, you multiply straight across. You end up multiplying 18 times 473. And then when you multiply 10 times 1,000, that actually gives us 10,000 in the denominator and 8,514 in the numerator, or 0.8514 in the 10 thousandths place. Cool. Okay, moving on to the powers of 10. So special note, powers of 10, they're special. When I multiply a number, a decimal in particular, by some multiple of 10, like 100 or 1,000, the multiplication is actually super easy. So the basic strategy when you multiply by powers of 10 is you move the decimal one space to the right for each power of 10. Which is actually really easy to see. Let me give an example. Let's say I have 3.014 times 100,000. I don't really have to figure out what power of 10 100,000 is, because all I really have to do is count how many zeros there are. Because there are 5 zeros in 100,000, that's 10 to the 5. So that means I have 5 tens, which means I'm going to move the decimal place 5 times to the right. So I'm going to take that 3.014 and I'm going to take the decimal and I'm going to go 1, 2, 3, 4, 5. And because I end up having 2 spaces extra, I will add zeros. So the final answer is 301400, and I'll just put my comma now, or 301,400. So we move the decimal 5 places based on the fact that this is 10 to the 5. And that's it. That's how you do. You don't have to do anything exciting, no multiplying. We can just move the decimal. Okay, now on to division. I'm sorry. It really is fighting me, and I don't know why. Division. There we go. Visual. Okay. Similar to multiplication, there are 2 representations we can use for division. The subtractive version, which is when you think of a subtracting multiple times. Okay. Let's look at that. Let's do 0.9 divided by 0.15. Okay. So here's how we have to do this. We have to start by drawing 0.9. Okay. Oops, I bumped something. And now the computer doesn't want to respond. There we go. Okay. 1, 2, 3, 5, 6, 7, 8, and 9. There we go. Shaded 9 of them. Okay. But what I want to do is I want to do a repeated subtraction of 15. So what I need to do, because that's 15 hundredths, is I need to go ahead and think of not 0.9, but 0.90. In other words, I should think of it in terms of hundredths as well, if I'm going to be doing as a repeated subtraction of 15 little hundredths. Okay, so here's how this works. Basically, I'm going to block off every 15 hundredths. Okay, so here's a 15 hundredths. 1, 2, 3, 4, 5. Yes. Come on, draw. There we go. There's a 15 hundredths. Okay, and then another 1500ths would be like right here, going the other direction. And then I can kind of keep repeating this pattern. And what I'm going to do is count how many groups I have left. So right now I'm at 4 groups of 1500ths. 5. And there it is, 6. And of course, if I had done a better job, it would be a lot clearer that I was done at that point. And there you go. All right, try to fill them in a little better. Okay, so we had 6 groups of 15, or I'm sorry, 6 groups of 1500ths. Oops, not thousands, 1500ths. And therefore, this equals 6. That's the subtractive approach, also known as partitive. That was the other phrase they used. The other approach is when you divide it up. Oh, wait, no, not partitive, measured. I think partitive is the one where we divide it up. Sorry, I mixed up those words. So the partitive approach is when we divide them up into groups. Wow, it does not want to let me write. Partitive. Thank you, kind computer. All right, let's do an example of that. I'll make it much quicker and easier. Let's do 0.8 divided by 4. So like the multiplication, because we have a whole number here, it is a little bit easier to do, breaking it up into groups. So I start by drawing 0.8. Thankfully, I don't have to do the 100 square. I can just do tenths. Trying to cut it in half. There we go. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That wasn't such a crappy line. It would look better. Okay. And then we will shade 8 of them. Okay. And then we will divide it into 4 groups. And each group is represented as 2 tenths. So each group contains 2 tenths. So 2 tenths is the answer. All right, let's do the pencil and paper algorithm. Similar to multiplication, we actually kind of divide like normal. The real trick with division is we never actually divide, or the divisor will never actually have a decimal in it. So we will move the decimal in the divisor. Move the decimal in the divisor, which also moves it in the dividend. Okay. Then divide normal. And then bring the decimal up. So different from multiplication, because division is done where you put your answer above, bring the decimal up. Okay, same kind of basic concept. So here, let me just show you an example of this so that we can kind of understand the big first step, which isn't as exciting as it sounds. 0.498 divided by 0.6. Okay, so in this problem, the 0.6, that's the divisor. That's the dividend. The divisor is the problem. We don't want a decimal in the divisor. So we move the decimal out of the divisor by literally moving it over 1, right 1. And because we're messing with it, we have to do that in the numerator. I'm sorry, in the dividend as well. We have to move the decimal once. So what we end up doing is taking 6 and dividing it into 4.98. So 6 goes into 49 8 times, which will be 48. And we will subtract and get 18. 6 goes into 18 3 times. And that'll give me 0. And then I just bring my decimal up. So 0.83. So the process of moving the decimal, really secretly what we're doing is multiplying by powers of 10. In this case, because we want 0.6 to no longer be 0.6, we want it to be a 6. We multiply it by a 10, and that moves the decimal once to the right. And then we have to do that to the dividend too. And we could do that when we have a division, because a division can be thought of as a fraction. 0.498 over 0.6. And we can multiply top and bottom by a common number. We also saw that trick too. We've been using that trick for mental calculations when we have done division and we've multiplied by something in both values. Okay, here, let's just do one more so that we feel good about that. Let's try 1.504 divided by 0.32. Okay, so I need to move the decimal twice in the divisor this time. So I'm going to move it twice in the dividend. So I'm going to divide 32 into 150.4. Okay, so 32 into 150. Well, I know that 3 into 150 goes 5 times, but I'm bigger than that, so I should probably go to 4. All right, so that's going to be 128. Subtracting is going to give me 22. 224. Okay, this I actually need my calculator for, but I did it earlier. So here I'm going to put the decimal up, and it comes out to, no, hold on. 7. It does come out to 7. I was going to say 7, but then I questioned myself. It does. It works. 224. Okay. Cool. 4.7. Yay. Put it below because I kind of put the division close. All right. And then lastly, just like with multiplication, when you have dividing by powers of 10, works in the reverse way it does for division. Powers of 10. So this time I'm not going to write out the rule. I'm just going to demonstrate it. So for instance, if I'm dividing 0.37 by 100, since there's 2 zeros, that's 2 tens. I'm going to move the decimal 2 places to the left because I'm dividing. I'm going the opposite direction. So I'm going to end up having to add a 0, 0.0, and then there's already a 0, and then 37. And there you go.